Hello, my name is Vladislav. I am an engineer of VTM Group company, and today you will see a balancing machine model 9D715US with drilling for unbalance correction module for balancing crankshafts. The machine is designed for balancing crankshafts weighing between 3 and 300 kilograms. The machine comes complete with crankshaft balancing prisms, roller cassettes, and plain textilite prisms. The machine consists of a base, which should be rigidly fixed on the concrete floor. If there are unevenness at the floor, it is necessary to use spacers. The machine also has a left measuring support, a right measuring support, safety mechanisms in the form of hinged brackets. Also the axle stops left and right. Support for fixing the rotation speed gauge. Belt drive. And the unbalance module, which consists of a base, supports, and a bed on which the drilling module is moved. Also the drilling unit. The drill is switched on with the power button. It is possible to adjust the drill's outreach, and it can be moved along the machine bed and set it to the required drilling position. There is also a height adjustment, which is done with this screw. Block height adjustment is provided on the supports. This is done in the following way: release these two handles and move the hand wheel by turning the hand wheel and move the screw up or down. After setting the required height, the handles are fixed in the reverse order. Also the axial stop is put through the ball. Here the ball is installed. The axial stop is placed in such a way that the center of the bearing falls on the ball. On the other side, the axial stop has a safety function. It is not in contact with the rotor. Also the supports can be moved along the bed. For this purpose it is necessary to loosen these locking handles, and with the help of a 19-spanner, turning this shaft, the gear will rotate, and with the help of the chain transmission the support will be moved along the bed. After setting the required distance between the supports must be fixed to the bed using these screws. The belt drive is moved in the same way. One lug is released, the second one, and the same with a 19-spanner. To move it we lower these clamps, and with a 19-spanner, rotating this shaft, we move the belt drive. After adjusting the belt drive to the necessary place on the bed, it is fixed with the same screws. The belt is tensioned using this hand wheel. If you need to tighten it more, a knob is provided here. Also here are these two rollers. They also move along these slots, which allows you to increase the girth diameter of the item being balanced. There are two straps that come with it. In the next section, we will look at the control cabinet with control panel. It is standing on legs that adjust its height. The optimum position of the cabinet is at an angle of 45 degrees to the bed, so that the operator is in a safe area when the workpiece is rotating, and so that he can visually monitor the rotation process and the indication on the console. So, the control cabinet consists of a housing, a panel with control buttons, and an industrial computer. A power switch and 2 lamps are provided on the side panel of the cabinet to signal the presence of voltage and the readiness of the drive. On the main push-button panel there are switches. The leftmost one is responsible for selecting the operating mode. It can be either manual or automatic. The direction of rotation of the rotor. Rotor turns. Rotor acceleration intensity, 3-stage switch. Rotor speed selection. Rotation start button and rotation stop button. In the upper part of the control cabinet there is an industrial computer on which the balancing program is pre-installed. In this case, the program is in German. A Polish, Ukrainian and also English version is also available. When the computer is switched on, the software is automatically started. To start balancing this crankshaft, enter the calculation mode. Select ISO accuracy class 16, set maximum rotational speed, set radii in the correction plane. Set the distance from the center of mass to the plane. Since crankshafts are basically symmetrical rotors, in this case 2 identical numbers different from 0 are set. It will also be necessary to set the mass of the rotor. It weighs about 40 kilos. Press the calculate button and we'll get the balancing tolerance. Next, we will press the accept button. And in this section, we're going to install the mass of our calibration weight. We use plasticine for this. Put it on his scale, we see that our calibration weight is 11 grams. Set it to 11 grams. Press accept. And then we do 3 launches. Select start without calibration weights, press the start rotation button. The rotor has started to turn. The next step is to press the measurement start button. We see the velocity. You can see the angle of the first and second planes, the value of the first and second planes, and wait for the stop button to activate. The stop button is active. After that we visually look at the stability of the angles and values. They're considered stable if the angles vary by less than plus or minus 5 degrees. Now everything is stable, we press the stop measurement button and the stop rotation button. Next, we choose to launch with a calibration weight on the first plane. Turn our rotor so that the contrast mark is vertically on top of the rotor. And fixing our weight on the cheek of the counterweight, also vertically at the top. Then we press the start rotation button and the measurement start button. Waiting for the stop button to activate. The stop button is active. Further, we look at the stability of the display of angles and values on the planes. Everything is stable. Press the stop measurement button and stop rotation. We select start with a weight on the second plane. Remove the weight from the first plane. And just like that, opposite the mark, put it on the second plane. Press the rotation start button and the measurement start button. The stop indication becomes active. Watch for stable display of angles and values. Angles are displayed stably, values are also displayed. Press the stop measurement button and stop rotation. Then press the button result. Save the rotor under any name. If you need to change the name, click on this box, enter the name and click confirm. Click Save. Next, we are shown the actual unbalance of the rotor without the calibration weight. Then to compensate for these 4 grams, you have to weigh them on a scale. That's 399, 398. Next, turn the rotor so that the orange pointer is opposite to the correction vector of the second plane. And place a weight vertically on top. Press the start rotation button. And we see that from the first plane the imbalance has decreased. The stop button became active, the angle does not change. Press the stop button. To switch to the drilling mode, it is necessary to set the method of correction to removal. And in the plane it will show. Similarly, bring the orange pointer opposite the unbalanced vector. And drill. The correction plane recalculation function will be useful for unbalanced correction on the crankshaft. It is activated by clicking on plane 1. In this function, we can see that we have some correction planes, which are marked with numbers 1 and 2. We can also move them to 4 possible variants according to the scheme. New correction planes are shown with numbers 1 and 2 with an asterisk icon. We select the necessary picture to transfer to where we will transfer them. To correct the imbalance on the second plane, we have no place to drill here. We can only drill to the left of the correction plane. So we're going to go with the picture 1, 2. And that's it. Choose picture number 1, for example. Set the radii according to the setting. Distance A. It's from the correction plane. 1 new to 1 old. It is 0, it does not change in any way. Distance B is the distance from the new first correction plane to the new second correction plane. We set it. (220 millimeters). And the distance C is from the old second correction plane to the new second correction plane. We have it set at 165 millimeters. 165. We press the confirm button and press the calculate button. Then we can see how much unbalance in grams we need to remove from the new second correction plane. How do we realize that this is a new correction plane? Because correction planes 1 and 2 are now written in italics and have asterisk icons. If we want to see what was there before, we just click on previous dimension, next dimension. We press the exit button, and correction planes return to the previous ones. Also, for recalculation in drilling depth, we enter the function mode. Select this function, the specific weight of the material, then we enter the maximum drilling depth. In the next column, we enter the radius of the test weight. In the column on the top right, we enter the diameter of the drill bit we are going to drill with. Here we enter the maximum number of points, or drill locations. And here the drilling radius is entered. After pressing the calculation button, we get point number and the depth to which it is necessary to drill. To generate a report after balancing, press Report. Create. Enter the operator's name, select Initial Startup. Final Start. Press the Create button. Report is generated, which you can save or print. The date is synchronized with the computer. To optimize the laser setting, a contrast mark should be made, preferably on a dark background. And set the switch, potentiometer, upper to position L. So that would mean that the light mark is now selected. And then turn the second potentiometer from minimum to maximum, until the orange indicator lights up, at which point the laser beam should shine on the mark. And rotate until the red indicator light comes on. After that, we make one complete revolution of the rotor, and see that there are no false alarms. If there are false alarms, we can reduce the sensitivity a little bit. We can turn it a little bit towards the minimum, and then we turn it again and make another full revolution. If there are still false alarms, you can change the angle of the sensor. Either the sensor distance or move to a different rotor plane, either up or down. The letter L is light and the letter D is dark. And in this case, we have a light marking, so the potentiometer looks towards the letter L. Anchor holes around the perimeter of the mounting leg are provided for mounting the drill module. They must be drilled at a certain distance from the machine bed. This distance will be indicated in the installation drawing. The next step is to drill the machine bed. This is the base to the floor. It will be drilled using these anchor holes. There are 3 points on each side. Shims can be placed under these places if there is a gap between the floor and the bed. These holes are used to transfer the machine. Steel rods or bars will be inserted here. They will then be used to sling the machine. The control cabinet is connected via the input cable on the right side of the control panel. This is where the motor, i.e. the actuator, is connected with the connector. The second connector is used to connect the drill module. It is optional. At the front there is an electric panel responsible for the drive of the machine. It's got a frequency converter, several power supplies, and a motor protection circuit breaker. The input cable is connected to the terminal box on the bottom left. 5 wires must be used for connection. which means 3 phases, earth and 0. The sensor cables fit to the back of the enclosure through a hole and a coupling. They are then lifted up and inserted into the appropriate connectors. All connectors are labeled. It will also be necessary to ground the metal hose using this enclosure here. So they're going to have to be placed under this comb, so that the metal duct ends at this point. This is the grounding bolt of the machine bed. The machine must be earthed. For this purpose, the grounding bolt on the electrical cabinet and the second bolt on the machine bed are used. They are grounded with different conductors to one common ground of the machine.